Some logarithms are easy to evaluate because they're perfect powers, like log base 2 of 4. We know that that's 2. And log base 3 of 27. We know that that's 3. But other logarithms are a little bit trickier to evaluate, so I have a strategy we can use. In Algebra 1, you solved exponential equations. For example, exponential, exponential. The bases are already the same. That means the exponents must also be the same value. So we can set up an equation by equating the exponents and solving for x. X is 5. That strategy can help us evaluate logarithms because we can rewrite a logarithmic expression as an exponential expression. So if I wanted to evaluate, we've already reviewed that this is equal to 3, but let me show you the new strategy. We're trying to find the exponent. So let's rewrite it as base 3 with an exponent of x, that's what we're looking for, equals 27. Then I also know that 27 is 3 cubed. Now that I have an exponential equation with both bases the same, I can see that the exponents must also be the same, so log base 3 of 27 is equal to 3. You don't have to use this strategy on easy logarithms, but on tougher ones you might want to. Like down here. Base 32, with what exponent, that's what we're looking for, is equal to 2. Let's rewrite 32 as 2 to the 5th power. And then we multiply exponents. Once the bases are the same, we equate the exponents and solve for x. Log base 32 of 2 is equal to 1/5. In other words, the 5th root of 32 is 2. On this one, base 1/2 would need what exponent, that's what we're looking for, to equal 8. I'm going to do property of exponents, make 1/2 2 to the negative 1, and at the same time make 8 2 cubed. Now that the bases are the same, we can equate the exponents to find that x is negative 3. We can also use the same strategy when we're given simple log equations and asked to find a missing value within the log equation. I'd start by rewriting the equation as an exponential equation. Base 1/2 with an exponent of negative 3 is equal to what? I'm going to use my property of exponents. This is 2 to the negative 1, which would eliminate the negative in the exponent. 2 cubed is 8. Number 2. Base 5 with an exponent of 4 equal to the argument. Well, look at that. The bases are already the same, so x must equal 4. Sometimes it's so much easier once you rewrite it as an exponential equation. Number 3, base x with an exponent of 1/2 is equal to the argument square root of 8. Well, guess what? A square root is an exponent of 1/2, and if we have matching exponents, logically the bases would have to be the same, and x equals 8. Last example, base root 5, exponent of 2 equals what? Well, we've got inverse operations right here, and the square root of 5 squared is just 5. So this is going to be a really handy strategy, rewriting logarithmics as exponentials throughout the rest of the unit.